Hello everybody, once again I am back with another video. We're going to be looking at more current density stuff out of NIFA, and in particular another configuration on how to solve for things like current density and your electric field and your potential, so on and so forth, when dealing with something that looks a little bit unique. So this is kind of a weird geometry, but I just want you to kind of imagine this with me here, okay? So what we have is we're looking at a cross-section of a cylinder, right? So, just so we can picture this better. So, here's the earth, it's grounded, here's your wire, and it's going out this way, facing towards you, or we're assuming it is. I don't know which way the current's moving at the moment, but let's just take current to be positive, whichever way we decide to orient it, right? So once we do that, we lay it in the earth and it's partially buried underneath all of this earth right here, right? So this is all also earth. Now, we have two conditions here that we want to look at whenever we're considering our electric field that is generated by this current, or by this wire that's running through the ground. I know Sunny Baby, she's like trying to give her input. I don't know if you heard her meow or not, but anyway. Yes, you are so knowledgeable, Sunny. She said it, not me. But anyway, so we have this set up, and we're like, okay, what the heck's our electric field? What are things we can discern from this particular configuration, right? So first and foremost, let's try and find our electric fields. Oh my goodness gracious, you know what? I'll just pick you up and I'll explain while I'm talking. She had to be in the video. Okay, anyway. So first and foremost, we have our simple Gauss's law that we applied in that very first example of current density, right? So along this surface, we know that the outer surface here is equal to some sort of enclosed current, right? So we do the dot product with n hat and dA, and because we're looking at the cross section of a cylinder, or in this case, the surface area is that of a sphere, and the surface area of not a sphere, I'm sorry, of a circle, basically, right? And that gives us 2 pi r squared. So we reorganize our terms, and what we get here is just that our current density at some radius r of this Gaussian surface we've drawn around our wire is equal to the current that's running through there divided by 2 pi r squared. Right, and then once again we just use our Ohm's law in order to reparameterize our expression in terms of the electric field, right? So we have our Ohm's law being E is equal to our current density divided by its conductivity, and we just basically plug in J, and then we just interchange the different conductivities for our electric fields for the different areas. And I think I kind of goofed up on that a little bit. I just wrote generically as R, but I don't think it necessarily has to be for this case. Let me check against my notes. No, I wrote R squared because I'm silly, but they should be the same, relatively speaking, at this boundary. But if you were to do it at some distance that wasn't R, we could do like outside of that we might have a radius B, or inside of it we might have like B minus R or something like that. So one of those kinds of distances. With that in mind, we know how to find our electric fields using Gauss's law for our current densities. All we need to do to find our potential V is by using that same integral expression we were doing again. However, because we are looking at 2 different areas with different conductivities, we need to split that integral up into 2 different pieces. The first of which being from B onwards to infinity, deep down under the earth, which really isn't infinity, but for sake of scale, it probably is. And then from A to our distance B, which is has a different conductivity altogether, right? So in this particular area, right? So this area has conductivity sigma C2, this area has conductivity sigma C1. So we plug those into our integral for our potential, and then we evaluate it from these distances. We get a term in the first integral that goes to 0, so we are just left with our current density magnitude basically multiplied by our, I don't think that needs to be squared. I might be dumb. Yes, I am dumb. I don't know why I wrote r squared in the denominator after evaluating it. My apologies. Some days are just a little bit stupid. I evaluated that term already. Grad student can't do calculus 2. It's always the little things, always the little things. Anyway, I looked at that and I'm like, wait a second. I just integrated that. Anyway, so we get our, basically our magnitude of our current density sans the r squared component multiplied by the inverse of the distance that it's supposed to cover, or the difference of those inverse, the difference between those inverse distances. So we do the same integral over here, 1 over a minus 1 over b, same story, right? And that's our potential for this particular configuration. Now, to keep things very simple and not as convoluted as the previous expression, because we know what our current is, and we're just calling that I, and we know what our potential is, we have V, we can use a much more familiar expression for resistance in order to solve for that, which is just our physics 2, V equals IR Ohm's law. I think I might, if I wanted to, give you a proof, but this result is actually just a consequence of our standard Ohm's law that we're using now for our current densities, right? That the V equals IR falls out of J equals sigma CE. But anyway, we just divide our potential by I, and we get basically the exact same expression, just sans the current term I. But yeah, once again, we use Gauss's law for our current densities to find the electric fields. Once we do some substitutions for each respective area for the electric fields, depending on the conductivities of that area. And then we apply our definition of our potential V as the negative of the integral from infinity to r of E dot dr. And we do that for both areas of our conductivity, right? We evaluate those, and then to get our resistance, we just use the classical V equals IR relationship to recover an expression for resistance of our wire. Yeah. Thank you very much for watching. Let me know what y'all think.